Okay, so now we are going to look at some special sets and some symbols that have been reserved for them. So let us start with, we have already come across this, the set P of all prime numbers. So we can write it in roster notation like this, the way we have already written previously. And so on. This is prime numbers. Then after this set, we have the set of natural numbers. Now when it comes to natural numbers, the old usage is to consider the positive integers. Okay, only the positive integers were considered to be natural numbers. But according to new usage, 0 is also included in this set. So sometimes you will see this symbol N denotes the set of all positive integers. However, sometimes you will find that the same symbol is denoting a set which has all the non-negative integers. That is, it starts with 0 and then goes on with the positive integers. So when you see this symbol, you have to make sure what meaning is attached to it. From the context you will know, or from the textbook that you are following, there it will be clearly stated what N stands for. But keep in mind that these special symbols, they have been reserved for these sets only. Although for this one, the meaning may slightly vary from text to text, but it is either this set or this set. Okay, so it has to be understood from the text which is using this set. Now after that we come to the set of integers. This also we can write in roster notation using ellipsis twice, -1, 0, 1, 2, etc. So these are all the non-fractional numbers that we have. These are integers. So these are natural numbers. Then these are integers. Then after that we get the set of the set of rational numbers. So here we can no longer write them, describe this set in roster notation. We have to take the help of set builder notation. And we know that these are numbers of the form A divided by B, such that A and B are integers, and this is very important, B is not equal to 0. So these are the rational numbers. Okay. So the thing here is that although we have written it in roster notation, in set builder notation, and we are saying that it cannot be conveniently written in roster notation, but there is a result which says that the rational numbers can somehow be enlisted just like these natural numbers. Now that result, however, is somewhat higher level, and we will understand that only when we get the concept of functions and one-to-one correspondence. So that will come later, and then we will see that the elements of Q can also be written like this. However, it's not immediate what pattern that will follow. Okay, that is a different matter. It is somewhat advanced, and for the time being, we assume that Q will always be written like this. Okay, then after that we get the set R of real numbers. Now here, if you can see that the way the sets are progressing, we are actually what are we doing actually? First we had all the prime numbers. Okay. After that we introduced some extra numbers and got the natural numbers. You can see that every prime number is also in this set. Okay. For example, 2 is here, you get 3 here, 5 also. Because this contains all the positive integers and natural numbers are in particular positive integers, so they are also contained in this set. Similarly, this set n is also contained in Z, this part. Okay, so here again we are introducing extra numbers, namely negative integers. Then also you can see that the set of rational numbers contains the integers, because you can consider numbers like this. If you take for example an integer 2, it can be written like this, 2 divided by 1. So it satisfies this form, 2 divided by 1, 2 and 1 are integers and 1 is not equal to 0. So every integer is also a rational number. Now, rational numbers are also contained in the set of real numbers. But however, you can see that I have not written R using, I have not described R using either roster notation or set builder notation. There's a reason for that. And the reason is that R can be defined only when we have the concept of limits of sequences, or something called the least upper bound property. So these things come from calculus and real analysis, which is yet to come. So for now, we just assume that the elements of R are known to us, that is, they are either rational numbers or irrational numbers. Apart from rational numbers, because every rational number is also a real number, there are irrational numbers. For example, square root of 2. This is a classic example of an irrational number. It is not rational. This can be proved, and in fact we will prove this at one point. So if you still go further along this line, you can have the set C of complex numbers. Okay, these things will come. Every real number is also a complex number, but there are some complex numbers, in fact many complex numbers which are not real numbers. And after that, you can still go on. There is no need to stop here. In fact, mathematicians have not stopped, and you can get another set like this, H. Now this set, it is called the set of real, let me write it here, real Quaternions. Now this is, although there is no need to show you this set at this level, but still I am showing. After Quaternions, now what these real Quaternions are, they are still some more numbers are there. The complex numbers are contained in this set, but there are more quaternions which are not complex numbers. Then you get octonions and so on and so forth. Okay, so let me also say something about these letters. These look like ordinary capital English letters, but they have been modified slightly. This way of writing, this style is called blackboard bold. What happens is that if you take a blackboard and you take a chalk piece, you hold the chalk piece horizontally and try to, for example, try to write P like this. Then you will get this pattern where one part is thicker than the other. You try to write N, then N, however, has to be written like this, then this. For Z or Z, again you write like this, and then this. For Q, you can similarly write. Okay, and then we have for R. For R, you can write like this, and this. Okay, how does Q come? Okay, anyway, you can figure out. Similarly, complex numbers and real quaternions. Now, P of course stands for prime, so that's why we have chosen P. N stands for natural number. What does Z stand for, and why are we using it to denote the set of integers? Z stands for the German word Zahlen. It means numbers. Now this has been used in this way because there have been many great German mathematicians who have contributed many things to mathematics. So that's why they use this. Q stands for quotient. Quotient of two integers. R of course stands for real numbers, C for complex numbers. Now this H, real quaternions, right? H is actually used because it honors the mathematician Sir William Rowan Hamilton, who introduced these real quaternions into mathematics. This number system is used at the time Hamilton introduced this. It was primarily used in mechanics, classical mechanics, but nowadays it is used in number theory, and it also serves as a classic example of something called a skew field in algebra, which we will come across, okay, in future. Now, the relationship between these sets, as we have already shown, it is this. The set of all prime numbers is a proper subset of the set of all natural numbers, which in turn is a proper subset of the set of all integers. This is again a proper subset of the set of all rational numbers, which is a proper subset of the reals, and the set of reals is a proper subset of the set of complex numbers, then quaternion, and it goes on like this. Okay, so this is the relationship between the sets. Now, these relationships can also be represented as pictures, some sort of schematic diagrams. They are called Venn diagrams. We will discuss them soon. Okay, now apart from these these sets that arise frequently in mathematics, there are some other types of sets that we should know about. An empty set is a set having no element. Now this may sound somewhat strange to you, that we are considering a set as a collection of objects. If there is no element to consider, why are we calling such a thing a set? But this is considered as a matter of convenience, much like how vacuously true statements are considered in mathematics. It also is somewhat similar to the concept of zero. You remember in our school, in elementary school, how are we taught about these numbers? 1, 2, 3, 1 apple, 2 bananas, things like that, right? As counting numbers. Now, 0 does not count anything. So, it is somewhat difficult to wrap our heads around that idea if we follow that route. That is, numbers are used for counting objects in a set. So, the situation here is similar. Empty set has nothing, so it is nonetheless considered to be a set which has no elements. Why it is considered, however, will be clear when we start to work with sets more and more. Okay, having no element, an empty set is also called a null set or a void set, because there is nothing in it. Okay. For example, the set of all elements in n such that x is less than 0. Now look at this set. In this set, this is the set of all natural numbers which are less than 0. Is there any natural number that is less than 0? If you recall, the set of natural numbers